I love playing RPG video games. There's something so satisfying about leveling up, unlocking new abilities, and taking on tougher challenges as you progress. It reminds me of how polyprotic acids work. Each proton is like a mini-boss, defeated, or in this case, donated in a specific order. You can't skip ahead to the final battle. You must remove each proton in steps. Just like in a game, progression is key. Esto es Real Chem. Titration isn't just about adding a base to neutralize an acid. It's a step-by-step journey to show how acids release their protons. Just like you defeat one mini-boss at a time in a video game, polyprotic acids give up their protons one at a time. Today, we'll explore polyprotic titration curves to see how these stages unfold and what they reveal about acid-base chemistry. Remember, when we add a strong base to a weak acid, the hydroxide ions in the base strip away a proton from the weak acid, converting it from the conjugate acid form HA to the conjugate base form A-. At the equivalence point, just enough base has been added to completely react with the acid, converting all of the weak acid to its conjugate base form. At the half equivalence point, we've added enough base to convert half of the weak acid to its conjugate base. This means the concentration of the conjugate acid and conjugate base are equal. As a result, at the half equivalence point, the pH is equal to the pKa of the weak acid. Here we have a molecule of citric acid. It may look more complicated than the acids we've seen so far, but it's actually just a polyprotic acid. Citric acid contains 3 carboxylic acid groups, and each of these groups has a labile proton that can participate in acid-base reaction. To simplify things, we can represent citric acid as H3A. When you titrate a polyprotic acid like citric acid, it loses its labile protons in stages. This means the easiest proton to remove is neutralized first, followed by the second, and then the third. Let's break it down visually to make it easier to understand. The titration happens in stages. H3A goes to H2A-. H2A- goes to HA2-. HA2- goes to A3-. Each of these stages has its own acid dissociation constant, Ka, and corresponding pKa value. The first stage is associated with Ka1 and pKa1. The second with Ka2 and pKa2, and the third with Ka3 and pKa3. These values tell us how easily each proton is lost during the titration. Here is the titration curve for adding a 3-molar solution of a strong base to 100 milliliters of a 1-molar solution of citric acid. At first glance, it looks more complicated than the titration curve for a monoprotic acid. But if we break it down, we can see that it consists of 3 distinct segments. Each segment resembles the titration of a monoprotic acid because citric acid loses its protons in stages. Each stage of the titration curve corresponds to the removal of 1 proton. In the first segment, we remove the first proton. As our base is added, hydroxide ions react with the citric acid H3A, gradually converting it to H2A-. This stage ends at the first equivalence point, where all of the H3A has been fully converted to H2A-. Midway through this process, at the halfway equivalence point, the concentrations of H3A and H2A- are equal. And the pH at this point corresponds to the first pKa of the citric acid. In the second segment, we remove the second proton. More base is added, converting H2A- to HA2-. The process continues until we reach the second equivalence point, where all of the H2A minus has been neutralized. At the half equivalence point, where H2A minus and HA2 minus are present in equal concentration, the pH is equal to the second pKa of citric acid. Finally, in the third segment, the last proton is removed. Additional base converts HA2 minus to A3 minus. This stage concludes at the third equivalence point, where all HA2 minus has been titrated. As with the previous stages, the half equivalence point occurs when equal amounts of HA2 minus and A3 minus exist, and the pH at this point corresponds to the third pKa of citric acid. Beyond the third equivalence point, there is no more labile protons left to remove, so any additional base causes a sharp increase in pH as the solution becomes dominated by the hydroxide ions. Now you can see how polyprotic acids titrate in distinct stages, each with its own equivalence and half equivalence points. By recognizing the stepwise nature of proton donation, we can make sense of the distinct regions in a polyprotic titration curve. Each proton is removed in sequence, with each step showing up as a distinct feature on the titration curve, helping us track exactly where we are in the process.